Thank you very much for the invitation. It's a pleasure to be here talking for the EPIC audience. First of all, I want to admit that we are not doing photonic computing, okay? We are doing something else. Is still related? Yes, because what we do is optical switching. At the end, we don't care about if the GPUs or XPUs are working in photonics or are working in electronics. We just process in optical. First of all, I would like to present to you our building block. What is the element? What is the core of our technology? So in this case, you can see here, this is a 2x2 multi-mode interferometer. You can see 2 input, 2 output. And we are building this in silicon photonics. So this is photonic integrated circuits, silicon photonics, and this is our tunable element. We are controlling this element using a thermo-optical phase shifter that allows us to reconfigure it in a microsecond reconfiguration time. Also, I would like to bring your attention that we are processing here in an analog way. So we can have this cross state, we can also have this bar state, but also we can also have this tunable coupler, which where we can just split the signal in two. We are going to get losses, of course, but well, this is a beam splitting of our signal in the two output ports. By putting many of these devices, many of these building blocks together in some kind of a mesh arrangement, we are creating this photonic layer. And all these thermo-optical phase shifters are controlled by a software, a dedicated software through the control electronics. So at the end, what we have is this one URAC product that we can use in data centers. Many of you will remember when we started at iPronics, we started doing a photonic FPGA, right? A photonic field programmable gate array. It was literally this. So what we were doing is to put all these elements in an hexagonal configuration. And with this type of devices, we were able to do whatever. So we were able to do filters, infinite input response, beam splitters, delay lines, any kind of photonic functions with some limitations, completely controlled by the in-house developed software. And we were also thinking about photonic computing. The issue was that we were running again and again the simulations, and we were seeing that with this, in particular with this configuration, we were not going to be competitive against an NVIDIA GPU for many years. So we really need to increase the integration of these let's say, to reduce the footprint of these elements, increase a lot the functionality per area in the chip, to be able with this type of technology to develop a photonic computer. But I see there are other mechanisms, right, able to do it. So then what we decided to do was an optical switch. So in this case, what we have done is that we have optimized this general programmable technology to develop an optical switch. In this case, in data center applications, it's going to be very important that it's lossless. So we added a disaggregated optical amplification step. The device is going to work in the entire O-band. It's designed to have a very flat response, a spectral response in the entire O-band. No electro-optical conversions, right? We process in the optical domain, and right now it has 32 radix, so 32 input, 32 output port, but we are planning extension of this running in the next periods. Fast reconfiguration time, low latency, right? The speed of light. And then we have developed a dedicated application programming interface. So now it's perfectly compatible with software-defined networks, and it can be controlled. You can control the device, that is layer 1 hardware in a data center, using the control plane, the same control plane that you are using for the rest of functions. Also, because it's photonic integrated, you can add some photodetector arrays. So we have photodetector arrays in the input ports, in the output ports of the chip, but also before the optical amplifier, after the optical amplifier. So yes, you can have completely control of the chip. Also, as I said, we can have this compensated multicast configuration in addition of the lossless point-to-point routing. Also, you can control the gain of the device. So it's not only that it's lossless, but also you can add 3 dB gain if it's interesting without impacting the bit error rate. Then regarding the telemetry, yes, so you can control everything that you want to control. And now let me just go through some of the applications. In data centers, we call scale out what is happening in the layers like the spine layer, the leaf layer, top of rack. This is the scale out of the network. Scale up is when we are talking about what is happening inside the rack. So we already, well, it's not that we identified, it's that the industry has identified a couple of applications for this scale out. In this case, the first application will be this failure resilience. This slide is based on an article from NVIDIA where they are using some of these MEMS-based devices for this failure resilience. So in this case, what they are doing is that they are connecting some of the ports of these OCS that are integrated between the layers of the data center with an spare switch. It can be also an spare rack. So then they recreate a failure in one of the NICs. And after this failure, they are able to reestablish the connection in 4 seconds. This happens because it's a MEMS-based device, so then it took 4 seconds. With one silicon photonic OCS, this will be much faster because they reconfigure much faster as the one that we are developing. Another important application right now is to be able to reconfigure the physical topology of the data center. So you can adapt it to different traffic demands. So in this case, well, as you know, these data centers are optimized right now for all-to-all traffic. But however, actual traffic patterns, they are showing spatial and temporal structures. With using an OCS, you are able to change this topology on demand, and this will be controlled by the SDN control plane. Finally, the scale-up networking. So what happens when you put OCS inside the rack? In this case, you can really increase the domain of the GPU, so you can put more GPUs inside your rack, increasing the efficiency of the training and reducing the time that is going to take. And in this case, you don't really need such a big radix OCS, but with a small radix OCS like the one that we are developing now, will be more than enough and more cost efficient. And just to finalize, this is what I was mentioning about the multicast. So because we are doing this analog operation, we are able to split, and even we are not even splitting 50-50, right? We can do 20-30 or whatever proportion that we want. And in this case, it will have a big impact if applied. It has a big impact in these strategies for training that like the data parallels, and we'll be able to do these data parallels without adding latency and reducing a lot power consumption. Yes, and that's it. Thank you very much.